I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is Two Leonardos. In 1202, Leonardo Pisano published a thick book titled Liber Abaci, the Book of Calculation. This book introduced much of Europe to the Hindu-Arabic number system with the special number 0 and showed how calculations were much easier with this system than with Roman numerals. Aren't you glad you don't have to do arithmetic with Roman numerals? This shows 52 divided by 13 equal to 4. We might all need IVs. Because the point of the book is to show how calculations are easily done in this new number system, Liber Abaci is loaded with problems requiring arithmetic. Some are bland, but many are interesting. One problem in particular caught the fancy of the mathematical world. A certain man had one pair of rabbits together in a certain enclosed place. One wishes to know how many are created from the pair in 1 year, when it is the nature of them in a single month to bear another pair, and in the second month those born to bear also. Because the above written pair in the first month bore, you will double it. There will be 2 pairs in 1 month. One of these, namely the first, bears in the second month, and thus there are in the second month 3 pairs. Of these in 1 month, 2 are pregnant, and in the third month, 2 pairs of rabbits are born, and thus there are 5 pairs in the month. Okay, let's go through this carefully. The graphic shows how the problem works. The first pair of rabbits, labeled 1, never dies. Each month they produce a new pair, labeled 2, 3, 4 as we go down. The second pair of rabbits grows into adulthood in month 2, then produces new pairs every month, for example, pair 5. Pair 3 grows up in month 3, but would then produce new pairs every month after that. We want to know how many pairs there are each month. Counting each month's total we have listed, we see 1, 2, 3, 5. That might be a surprise after 1, 2, 3. If you continue to track the rabbits month by month, you'll get 8 next, then 13, and then 21. Do you see the pattern? 1, 2, 3, 5, 8, 13, 21. It looks like the next number is the sum of the previous 2. That would make the following number 34, then 55, and so on. We call this sequence of numbers the Fibonacci sequence. Well, actually, there are several why questions we want to answer. Leonardo Pisano, the author of Liber Abaci, was of the Fibonacci family, and so became known as Fibonacci, son of the Fibonacci family. Why does that addition rule always work? The next month's population is the previous month's population plus new births. New births come from adults. And now the key step. The adults at month 5 are the pairs who were alive, adult or not, at month 3. So the next population, month n, is the existing population, month n minus 1, plus the newborns, and that equals the population the month before that, month n minus 2. The pattern holds. Why would such an odd little problem and its sequence of values become famous? And they are very famous. There is an International Fibonacci Association with regular meetings, a Fibonacci quarterly journal publishing high-quality articles, and the list goes on. I have a clock that's based on the Fibonacci spiral. Like numbers such as pi and e, the Fibonacci numbers have an uncanny way of appearing in unexpected settings. The number of petals on a flower is often a Fibonacci number. A 4-leaf clover is rare and lucky because most clovers are 3-leaved Fibonacci number. There are typically 5 petals on a buttercup, 8 petals on delphiniums, and so on. Flowers that grow in spirals almost always have Fibonacci numbers because the spacing that maximizes sunlight to each petal generates those values. Speaking of spirals, count the spirals on a pine cone. You'll find 5 in one direction and 8 in the other. Count the spirals on a sunflower. You'll usually find 21 or 34 or 55, all of which are Fibonacci numbers. If you compute ratios of consecutive Fibonacci numbers, so 5 over 3, 8 over 5, and so on, you'll find ratios that quickly get stuck on the number 1.618. Now, the exact value of this irrational number, which is usually denoted by phi, is 1 plus square root of 5 over 2, and is called the golden ratio. It is said to be behind many architectural structures, for example, the Parthenon, and paintings. Leonardo DaVinci's Last Supper is famously described in the movie The Da Vinci Code. Notice the spiral on this overlay of the Last Supper. There is a large mythology around the golden ratio, so you may read such facts as books and cereal boxes are in the golden ratio because it is the rectangle that is most pleasing to the eye. If you like this idea, don't take out a ruler and check. You'll be disappointed. This book is 9.5 by 6.5, which is 1.46, a pretty long way from 1.62. Take a step further. The ratio of head height to head width is supposed to be the golden ratio in attractive people. How would you define head height, for example? If you include enough hair or not, you should be able to find a way to measure yourself and find out that you are, in fact, perfect. There are a lot of great mathematical facts about Fibonacci numbers, apart from whatever mystical sway they hold over nature. One example is the formula f sub 2n plus 2 equals f sub n plus 2 squared minus f sub n squared. That's a lot of notation. Let's see what it's talking about. Let's use n equals 5 as an example. So on the left is f sub 12. 2n plus 2 is 2 times 5 plus 2, 12. And that means the 12th Fibonacci number, which is 144. On the right, we have f sub 7, 5 plus 2. The 7th Fibonacci number is 13. The 5th Fibonacci number is 5. So the right-hand side is 13 squared minus 5 squared. That's 169 minus 25. And that's 144. Exactly f sub 12. Pretty amazing. There are numerous excellent books and websites to help you explore the Fibonacci sequence and the golden ratio. In particular, anything involving Art Benjamin's going to be good. Have fun.